In this video, we have a closer look at the famous complexity classes P and NP. And I will show you how you will be able to gain $1 million after seeing this video. So what we consider is time complexity, and the classes we are looking at is P and NP. We start with P. P is the class of languages that are decidable by, now the most important word is a deterministic. Turing machine in polynomial time. So this is P, class of all languages that are decidable by a deterministic Turing machine in polynomial time. We consider here in this introduction to complexity, we consider yes-no problems. So these yes-no problems are again encoded in languages. So we would like to decide languages and formulate our problems in terms of languages. Some very simple examples of languages that are actually decidable in polynomial time are, of course, regular languages. All the regular languages, so examples, are the regular languages. All the regular languages can be decided by a Turing machine in polynomial time just by scanning the input from left to right and changing states accordingly. And then we just need to scan each letter only once. So we have linear time. Linear time is of course polynomial, so all the regular languages are in P. Even the context-free languages, they are as well in P, context-free languages. This is something I will not prove. There are algorithms that can solve the membership problem in polynomial time, even for the context-free languages. Okay, there are a lot of other problems that are actually in P. The second class we're looking at is NP. And NP is the class of languages that are decidable by a non-deterministic Turing machine. And again in polynomial time. Polynomial time is always something like O of n to the power of k or something. It's the same for both cases. So. And there are also a lot of interesting problems that are in NP. For example, one famous problem we will be looking at will be the satisfiability problem of propositional logic. Sounds quite abstract, but actually it's quite important. Also the problem whether a graph has a Hamilton circle, the so-called traveling salesman problem, graph coloring, problem clicker, check whether a graph has a subgraph that's actually a clicker. There are a lot of problems that are in NP that are highly relevant in practice. For example, Hamilton is the question: you have a graph and you want to visit each node only once. And you would like to get a circle of a certain length. And the question is there such a Hamilton circle in the graph? And that relates, of course, to transportation problems, to logistic problems. When you have a car that has to visit a certain number of clients. So these planning problems, many of these problems are in NP. So they can be decided by a non-deterministic Turing machine, and this non-deterministic Turing machine will simply guess one solution and then check whether the solution is actually okay. So the approach is typically by guess and check. Guess and check. Now, apparently, every deterministic Turing machine is also a non-deterministic Turing machine. So we know that all the languages that are decidable by a deterministic Turing machine are also decidable by non-deterministic Turing machines. So it's clear that P is a subset of NP. That's clear. However, the open question is whether P equals NP. This is actually an open problem. Something nobody knows so far. This is open. If P equals NP, this would mean that we might get efficient algorithms for all these relevant problems. If it's not, so if P is not equal to NP, then there might be no really efficient problems that solve efficient algorithms for these problems, and we might have to do with heuristics. So this is actually an open problem, and now back to the promise from the beginning. This is one of the Millennium problems, and if you happen to have an idea how to prove it, that P equals NP, or maybe that P is not equal to NP, doesn't matter, you will get actually a reward of $1 million. So this is an interesting and still open problem.